Aloha everybody, this is Gigi. I am from Kauai Community College. This video is on the extreme value theorem, meaning we are going to use the extreme value theorem to find the absolute maximum and minimum of a function. So, suppose the theorem says that if a function is continuous on a closed interval, if the function is continuous on a closed interval, for example, let's take a look at the one on the left-hand side. Closed interval AB. Okay, so here's A, here's B, and we're looking at the closed interval AB. And the pink function here, okay, so that's continuous. If it's continuous and we're looking at it within a closed interval, what can happen? It will have an absolute maximum and an absolute minimum. So looking at this, the absolute maximum is at the left endpoint and the absolute minimum is at the right endpoint. But does it have to be at the endpoint? No. Okay, so for example, let's take a look on the one on the right. So we have a closed interval AB. The function, so a closed interval AB. The function is continuous. Okay, so the conditions are met in the theorem. Then the theorem suggests that it will have an absolute maximum and an absolute minimum. So here is the absolute maximum, and here is the absolute minimum. Okay, so again, the extreme value theorem says that if a function is continuous in a closed interval, then it will have an absolute max and an absolute min. Here is an example. Suppose we have a function, f of x is x to the fourth power minus 2x to the third. This is a polynomial function, and we know that the polynomial function is continuous, and we do have a closed interval here from -2 to 2. Continuous and closed interval will tell us that it will have absolute max and an absolute minimum. Well, how do we know where they are? Well, first of all, if there were going to be an absolute max and min, they would be either at the endpoint or at the critical points. Okay, so let's go ahead and take the derivative. The derivative is 4x to the third minus 6x squared. Then we can factor to solve. The derivative here is always defined, so we don't need to worry about when the derivative doesn't exist. We do need to look at when the derivative is 0. Derivative is 0 when this is 0, and also when this is 0. Okay, so you have two solutions. Your critical points are going to be at 0 or 3/2. And what are we going to do with the critical points? We will put them on a number line, and then we will test the intervals in between. If there's a sign change, then we know that those are going to be our relative max or relative min. Then we're going to compare the values to see where the absolute max and min are. Okay, so here we go. Let's check. The derivative evaluated at -1 is negative. Okay, so the first part is positive always because we have 2x squared. Square a number, it's going to be positive. And then when x is -1, 2 times -1 minus 3 is a negative number, so the product is negative. All right. Now, in between 0 and 3/2, let's just pick 1. Again, the first part is always positive. The second part, when x is 1, 2 times 1 minus 3 is a negative number. So we still have a negative derivative here. That means the function is going to continue to decrease. That means there at 0, no extreme value. Then let's pick a number to the right, say 5, way out there. The first factor is 0. The second factor, 5 times 2 is 10 minus 5 is positive. So the product is positive. Our function is increasing on the right of 3 over 2. So we have a relative minimum at 3 over 2. Okay? So we are talking about a continuous function on a closed interval, negative 2 to 2. So if there were an absolute max and absolute min, it will happen there, here, or here. Okay, at those relative min, max, or the endpoint. What are we going to do to check? Find out what the function value is at those points. So on the left endpoint, f of negative 2 turns out to be negative 56. F of 3 over 2 is 0. And f of 2 is 8. So comparing those two values, this is the lowest and this is the highest in that closed interval. So we would say that the absolute maximum is 8, and that happened when x equal to 2. The absolute minimum is negative 56, and that happens when x is negative 2. So in this case, the absolute max and min happen at the endpoint. Does it have to be the case? Nope. Okay, so we are going to go ahead and take a look at another one and see. F of x is x to the 2/3 times 2 minus x. When we take the derivative here, well, we could use the product, or we could distribute this in and then not use the product. When you distribute x to the 2/3, and you will get 2x to the 2/3 minus x to the 5/3. 1 plus 2/3 is 5/3. So then we would say the derivative here is, we just go ahead and use that power rule for taking the derivative. 2/3 move down, that would be 4/3 minus 1, x is negative, x to the negative 1/3, minus 5/3, x to the 5/3 minus 1 is 2/3. And then we actually rewrite this as positive exponent and get a common denominator, we would say that f prime of x, which is the derivative, is 4 minus 5x over 3 cube root of x. Now, this, when we're looking at the critical point, this is undefined when x is 0. Okay, so we would say the critical points are at 0 or 4 over 5. 4 over 5 is when the derivative is equal to 0. So for x, we get 4 over 5, right? F prime of x equal to 0 when x is 4 over 5. Okay, so those are our critical points. Put the critical points on the number line. And we're going to check on the derivative in between to see if there's a sign change. The derivative when x is negative 1, the numerator is going to be a positive number because negative 1 multiplied by negative 5 is positive 5. And then plus 4 is 9. So, and then the denominator is negative because cube root of a negative number is a negative number. That means the quotient is negative. Your function is decreasing on the left of 0. Pick a number between 0 and 4/5. Well, let's say 3/5. 3/5 multiplied by 5 is 3. 4 minus 3 is 1. That's positive. On the denominator, cube root of a positive number is a positive number still. So we have the quotient being positive. We have a sign change. Decreasing and then increasing. That tells you this 0 is where a relative minimum might happen. The derivative evaluated at 2 to the right is negative. So your function is increasing on the left of 4/5 and then decreasing on the right. That means 4/5 is where the relative maximum happens. So you have a relative max, a relative min, and we are considering the closed interval between -1 and 2. So where could the absolute minimum happen? It could be at the endpoint, or it could be at the relative max or min. How do we know? We just go and check the function values. F of 1, when you do the calculation, -1, when you do the calculations, you'll get 3. F of 0 is 0. F of 4/5, which is 0.8, is approximately 1.034. And then F of 2 at the right hand point is 0. So as you can see, 0 is your lowest function value within the interval. And F of -1, which equal to 3, would be your highest within function value within that interval. So we would say the absolute maximum is 3, and that occurs at x equal to -1. And then the max absolute minimum is 0, and that absolute minimum happens in 2 places. At 0, at x equal to 0, and then also at x is equal to 2. Okay, but the absolute minimum, there is only one absolute minimum, and that is 0. And that is it for the extreme value theorem. Again, what kind of function are we looking for? We're looking for continuous function. That's the first condition. And the second condition is you must be looking in a closed interval. Okay, so in order to conclude that it has an absolute max and an absolute min, you need to have these 2 conditions checked.